So I'm Jason Oberg. I'm one of the founders and CEO of Tortuga Logic. We're a hardware security company based here in Silicon Valley. I'm going to talk today a bit about some of the security verification work we're doing around RISC-V and some of the opportunities that I see there as well. I think this is kind of redundant for many in here, but there's obviously a lot of growing popularity of RISC-V in a variety of applications, right? So we're seeing a lot of companies downstairs with custom AI accelerators, uses on the IoT edge, storage devices, compute in the data center, graphics, and many others, right? We're seeing a lot of, obviously, in this track, a lot of security-based applications of RISC-V as well. I think many know, but many might not know, but RISC-V itself, by design, does not standardize or provide any guidance around specifically implementations. And so when you actually are, and that's the whole purpose of RISC-V. It's open, you can follow the ISA spec, and you're free to build whatever you want. And this is obviously very powerful because you get this broad flexibility. But with this flexibility, obviously has, you have this fragmentation, and there's not a lot of core security guidance, I would say, around what can get created. And so there's potential for, let's say, insecure side effects from this approach. And I would talk about some of the opportunities and things that we can do there as a community. And I think based on I wasn't sure what the audience would be here, and I think based on the prior talks, this is probably, I think most people understand this, but I'm going to say it anyway. But there's this notion of architecture versus microarchitecture, right? And so RISC-V is an ISA. It's an instruction set architecture. It specifies, an ISA in general is this would say a timing independent functionality of the processor, right? It's the contract with how the software will actually execute on the real hardware. And realizations of this ISA are, you can refer to them as implementations. So when you actually go and implement an ISA, you start actually building a processor design. You're going to add a bunch of different features from the microarchitectural standpoint, right? So this is the specific features that get added for how the actual implementation is created. And so from an ISA perspective, it just defines the inputs and outputs. It defines what your program will do, but it really doesn't specify anything else. And so right here, here on the right side, obviously, is a lot of existing cores based on RISC-V. There's many others that folks have had. But they're all based on the RISC-V ISA, but they're very different implementations. And so I think that's a key distinction to remember that this ISA versus implementations. So at the microarchitecture thing is where things are actually built, right? So this is where things like caches are added, branch predictors. You have speculative execution, prefetching, out-of-order execution. You might add some cryptographic acceleration. You might even add hardware memory protection units. The list goes on and on and on. And so all these structures by design are hidden from the software developer's point of view, right? It doesn't add any value, or if you're trying to optimize for performance, it might add some value to know that the cache is there in some respects, but it doesn't change your program's behavior to know that these are there. And so these are obviously added for performance, for efficiency, for example, doing cryptographic operations, and hardware is both faster and more power efficient. And then you add a lot of different features for security, right? Memory protection units and these type of things. And so it's important to remember that when you actually implement something, you can actually violate a lot of system security requirements. And so even if the ISA is sound and the actual implementation matches that, you could still have some vulnerabilities that are in your design. I think this has been reiterated a lot here, which is very good. But I think this gets lost in a lot of discussions that security is a system level property. Conventionally, we were worried about things very higher in the computing stack, and that's where the attack points were. And I think by design, we always are reactive. You're attacking this thing, let's go chase that thing. You're attacking this thing, let's go chase that thing. Fortunately, people are attacking hardware now, so we're chasing that thing. But each layer of the computing stack relies on the layers below it, right, from a security perspective. And so there was a past misconception that hardware was secure. It was the secure base. But as we know, a lot of the recent microarchitectural design choices and the actual implementations of designs have caused, I would say, more system-level types of exploits. And these are really highlighted by a lot of these recent attacks that show that if you find a vulnerability at the lowest levels, you can compromise the whole system, right? And even worse so, as you get farther to the right, it's more cost-effective to fix than if you're farther on the left, right? If you have something baked into ROM code or into actual RTL in your part, you can't patch that, right? And as things get bigger and bigger, it gets to be easier, but at the same time, you can have significant vulnerabilities that can pop up in the hardware. And so I feel like I'm a broken record here talking about Meltdown and Spectre, because I think a lot of I don't know, I'd say 95% of the talks in this whole session have mentioned this, but there's been a lot of other, this is historically has been going on. I think this has brought a lot of awareness, but the year before, even in a Wired article, there was a group of researchers that found you could use a side channel, microarchitectural side channel memory management unit to get around address space layout randomization, for example. There's been a lot of other these types of hardware-based attacks. Cache timing side channel has been around for a long time. The key point here is obviously vulnerable hardware enables these system-level exploits, right? It's not, and these aren't just compromising just the hardware, it's compromising the whole system by exploiting these. There's been many, many variants of obviously Meltdown and Spectre since the first attacks came out. And again, I think many of you will know this, but just to dig deep a little bit more about how these attacks work and how these were applied, and then getting into some of the applications into the RISC-V design helps to understand first, memory hierarchy and processors, how these side channels worked. And so the general premise, right, is going to doing a memory access that has to go to main memory, or worst case into disk, is really, really, really slow. And so modern processors all use caching, or most do, to help speed up your memory accesses. And so cache is essentially a smaller memory that has fast access time and will store data in it that's been more or less accessed most recently or the most frequently. And there's predictive things that are involved in that. But just simplistically, that's what happens. A cache hit is essentially the concept of when something's in the cache, it's fast. When you access it, it's in the cache. You can say this is a cache hit. If it's not in the cache, it's slow, and you can easily measure these. It's an order of magnitude slower if your data is not in the cache. So you can easily measure a cache hit versus a cache miss. This is important for some of these attacks. Really, the fundamental problem with these vulnerabilities is that they exploited the implementation, right? So from an ISA level, there's really no problem here, right? It's the actual implementation of these microarchitectural features. And so the attacks show that essentially unauthorized, what I'd say, information can be observed via caches and speculative execution, and there's an opportunity to observe these for a lot of different other microarchitectural features. And so, for example, a lot of these attacks looked at extracting kernel memory and these type of things from modes and privilege levels that should not have been able to access that data from. I'm going to go through this in a bit to show you kind of how this can get applied, and then get into some of the use of our products in this domain. But in general, to give you some overview of how this attack works, imagine the attacker has the ability to execute this block of code, which is just pretty straightforward block of code. And the attacker goes and sets X way out of bounds. And it sets X to a point where array 1 will actually be accessing data that's in, for example, kernel memory. And so the attacker will run this code. This won't execute because X is way out of bounds. The system or the microarchitecture features will say, I think this is going to work. I'm going to try to run this code. You'll get a segmentation fault or an exception. And from a program semantic standpoint, Y never gets that value. Your program crashes or something else happens. But the problem is the actual cache got filled with all that information. The microarchitectural state changed because of that. And essentially, because array 1 of X is the address into array 2, the actual cache line is directly related to the value of return from array 1, which if that points to kernel memory, you can actually infer this by actually just accessing certain cache lines. And so if you access a particular cache line and the access is fast, you have an indication of whether that data was actually brought in from the speculative execution or not, and you can infer actually the value of array 1 from these accesses. And so at the heart of these attacks, there's a lot of other variants that go on in these, but at the heart of these, this is what was exploited, is this notion of leveraging the speculative execution and these timing variations, and then measuring those via these indirect leakages. And so to ground this a bit more so you can understand kind of how this gets applied and the ramifications for RISC-V and moving forward, give you a very concrete example. Imagine you're running a encryption algorithm. You have two modes, RISC-V, or I think there's I believe there's 3 modes. You have your user mode, you have your supervisor mode, machine mode. So imagine in machine mode, you're going to run some encryption algorithm. Imagine it's a block cipher. Let's say it's AES. Right? AES is public. The actual lookup tables and so on used by this are completely visible by anybody. Which I have there is this T buffer, for example, this T lookup table. But the whole point here is you want to make sure that obviously the key is secret. That's the whole basis of how encryption works. And so imagine you have multiple privilege levels here running, and the machine mode is going to run this code. You want to be able to see if the user can actually learn information about what the key is after the machine mode runs. Imagine the user mode goes and runs. On the RISC-V design, you go and you run this, and you see You do the access patterns of all elements of this buffer T, for example, or this lookup table T, and you time that for all the accesses in the cache. And you'll see the attacker or the user mode will be able to easily measure what a fast access looks like. Then the machine mode can go then and run. It'll run this encryption algorithm, it'll with a secret key as an input. And what will happen is some of the state of that system will change, right? So you have a set of cache lines that are evicted because now they were related to this machine mode. The user mode could then go and run, retime all of those, and easily indicate that this line T of 1, when it did T of 1, that ended up being slower. And so when it ended up being slower, I actually learned that 1 is the value of the key for the machine mode. And so there's a lot of different variants that you can do this, and this is obviously a simple example, but at the root of all these attacks that have been done are based on this concept of measuring fundamentally microarchitectural leakages, either direct or indirectly, via the behavior of the underlying hardware, because they're shared between multiple levels of trust at a software level. And so there's obviously many others. I've kind of been talking just about these, but in terms of implementation issues, and as I mentioned, just to reiterate, the big gap I see that needs to be addressed is from the ISA perspective, you can build a lot of hardened security, but as you get into the real implementations and as people make custom implementations, there's a lot of opportunities to get a lot of these wrong. And so these are some use cases that a lot of our customers are using, but hardware roots of trust, system-on-chip access control, several 100 million gate designs and how your cores interact. I mentioned side channels and so on. External debug, third-party IP, which is a big concern in a lot of the government communities. There's a lot of opportunities for implementation issues at these levels. And I think one of the key components too, as I mentioned this in the beginning, security is a system-level property, right? And so these issues span both hardware and software, right? If you look at something like a Meltdown Spectre microarchitectural attack, there was code running there. It wasn't just, if you look at the generated RTL for RISC-V core, or for the x86 core or the ARM core in the attacks, you could argue that there's no side channel issues without actually executing any code on them. It's when the actual software is running on it is when you have a vulnerability, those two running together. And so that's really what we're focusing on, is helping verify some of these system-level security mechanisms. We're doing so in a way that helps leverage your existing verification efforts. So the first step to using our products is the specification of a threat model. And so there's no way to ever prove you're fully secure. And so adding things like microarchitectural side channels to your threat model, adding things around how your encryption keys are being managed, and so on. We have a way of expressing what assets you're trying to protect are. So we have a way of defining what your threat model is. The next step is we take as input your actual design files, and so with the actual generated RTL. And I know a lot of the community here is looking very much at a lot of formal-based techniques, which I think are extremely valuable in verifying the correctness of the RTL that's generated, and then also guaranteeing the security fundamentals of that RTL. But then as it gets integrated into a bigger system with software and so on, is really where a lot of this is deployed. But that RTL, your design files, the generated RTL, whether it's from a chisel flow or what have you, and the threat model are loaded into our platform to generate a synthesizable piece of hardware IP. We call it our security model design. This embodies a lot of our information flow technology, and we're able to track assets and so on. And then you can take the security model design and insert it into your existing functional verification flows. And so these are the existing EDA tools that the industry is using to build chips. So these are the formal verification tools from Cadence, Synopsys, and Mentor Graphics, for example. Your simulation environments, these are the hardware RTL-based simulation environments, or the hardware emulation environments. These are the Cadence Palladiums, the Mentor Velocis. These are large hardware emulation environments or FPGA-based prototyping environments. And so you could take the security model design and run it with those existing RTL, the existing design files in those environments. And then our Unison product focuses on just running these in the simulation environments. And the key component here is, like I mentioned before, system-level verification around hardware and software. And the last step is you can analyze the results. So based on the results that you get, you can import this into some of our platforms and look at the results. To walk you through a bit of that a little bit more pictorially, as I mentioned before, the first expression of this is the specification of these security rules. One of the big goals that we have is to create some of these security rules for the RISC-V community, so that when you actually are going to build an implementation, you have a set of fixed rules that you can then take and apply to say, when I implement my RISC-V design, I run a software configuration, I don't have a cache side channel. And so we can help provide that framework for you to verify within your existing functional verification flows. But these are first created. These can be custom or they can be fixed, as I mentioned, for a particular IP. And then we're working towards creating some of that. We then provide a platform that generates our security model design. This is Verilog IP. So this is just a set of Verilog files that you can then run alongside in your existing verification environment. So if you already have a flow in place for testing your designs to make sure they work correctly, we can feed into those existing flows. And it's whether it's formal simulation, emulation, whatever you may be doing. It's passive, so it doesn't disrupt the current engineering cycles and so on that you're currently under. And then the last step is we have a way of analyzing the results. So we have an analysis platform, and I'll show an example of this with the RISC-V rocket from GitHub, some analysis that we've done there. But it helps you identify mismanagement of your assets, potential violations, and so on. So to go through a quick example here, so we had a demo. I think the exhibit hall's over now, so if you didn't see this, we can set up a time. I'm happy to show this afterwards. But we have the RISC-V core running. We have the base test cases all up and running, the verification environment, and have that whole flow up and running. We were able to validate or identify side channel leakages through the cache, which is not surprising because caches themselves by nature have timing side channels. This should not be a surprise. But we're able to easily show that there's leakages through the cache in the rocket. The way this worked is essentially I have a very, very simple block diagram of the cache. The actual data cache in the rocket has more inputs than that. But there's a write data input. There's a W mode input that says that you're doing a write. And then there's the output data when you're actually reading data from the cache. And so one of the security properties we have here, as I mentioned, you want to potentially have isolation both in timing as well as direct leakages in the cache. The security property here on this top line says start basically tracking that W data as it gets written into the cache. So this says start tracking this input data when you're actually doing a write and when you're in a machine mode. And so data will get monitored and observed and tracked once it's actually written in machine mode. And then you want to make sure that data never leaves the cache unless you're still in machine mode. And so obviously machine mode could read its own data and observe its own data. And obviously from a side channel perspective, observe itself as well. But if it can infer that if the mode changes and that written information is observable at that output, then that would be bad, potentially, right? So if you're concerned about either direct access or if you're concerned about side channels as well, or timing side channels, and we can detect those variants as well, and I'll show here on this next slide. So this is our user interface. This is one of our views. We have two views. We have our waveform view, which will look a lot like what you'd see from a normal simulation view if you're using RTL-based simulation. And then we also have a path view, which actually shows a leakage path throughout your actual design hierarchy. But what's happening here is that this little red shading actually shows what signal, in this case, belongs to machine mode. And so you can see there's a write transaction, and we're actually writing red data into the cache. You'll see that the mode then changes. This privilege mode here, 3 is machine mode, and we switch to user mode. And then here at the output, we can actually see that a lot of this information is actually leaking to a lot of the outputs of the cache. And so we're actually able to infer the data that was written into the cache at the actual external output when you're in a different mode. And so the data that was written here in machine mode is observable by user mode, even though that the values did not change. So user mode did not read the values directly. It actually inferred that information, and that's what this red shading here is indicating. The open source nature of RISC-V, I think, is obviously very powerful. It provides wide flexibility. I think a lot of the emphasis on a lot of the formal efforts are going to help resolve a lot of these issues as well, because you get this fragmentation. You want to be able to verify that from both a functionality and a security perspective that you're implementing that ISA properly. But as your systems get bigger, as you're running more software, and as your state gets much larger, it's important to remember security is a system level property. And so just looking at things from the ISA upward and so on, from a system design perspective, isn't going to get you the security you want. And that's what many of these vulnerabilities really showed. And so we have a framework that's commercially available. We've deployed this on several 100 million gate SoC designs, very complex designs and it scales well to many of these. So one of the big initiatives that we have is helping create this framework around the implementations. And so we're Fortunate to be a part of the Security Standing Committee, and I think that there's opportunities for, I would say, standardization, at least guidance, and I think some of the formal work will help drive a lot of this as well. But helping create a set of sort of implementation best practices for security as people take the ISA and start building their own stuff.